Good morning. Welcome, everybody. I'm Dan Kurger, and I'll be your MC today. Today's webinar will walk you through superelements and how you can use them in your analyses. Our host will be George Antoon, one of our superelements experts here at ATA. And before I turn it over to George, though, let me give you a real brief intro to all of us here at ATA. So most of you know ATA either through our role as a Siemens partner and reseller or through our robust engineering services. It's our experience in providing engineering services across a wide range of industries that allows us to put the value added, if you will, in value added reseller. Solving many of the same issues in the same industries as our software customers allows us to provide exemplary support. On the services side, our focus is really on analysis and test-driven design. Whether it's performing ground vibration tests on state-of-the-art aircraft, or analyzing the next generation of spacecraft and planetary rovers, or helping to ensure the safety of roller coasters and other entertainment park attractions, ATA is here to help our customers meet their toughest engineering challenges. And of course, being experts with Siemens PLM software helps us do precisely that. Speaking of using that software, here are the Siemens product lines that we use and can help you out with, whether through its license sales and technical support or by training your engineers to use these tools to their fullest capacity. Note the recent addition of SimCenter, which was formerly known as NX but in the wake of several Siemens acquisitions, also incorporates tools from LMS and CD Adapco. But for more on that, you'll have to tune in to the next webinar. I'd also like to point out that ATA developed the training for NX Nastran and are recognized for our unique depth of experience with this solver. We host a variety of classes ranging from introductions to FEMAP or FEA in general to dynamic response, superelements, optimization, the list goes on and on. You can find a full listing of the available classes we have on our website. Speaking of websites, many of you have already seen this site, and here you'll find software product information, links to download free trials, info on our upcoming training classes, more and more. For existing users, you'll find a link to our technical support hotline and an ever-expanding array of free resources from white papers and training videos to tutorials and free APIs. I invite you to check out all these resources after the webinar. But without further delay, I'd like to turn it over to George for the main event. George, take it away.
Thanks, Dan. So as Dan mentioned, my role at ATA is that I'm primarily a project engineer, so I spend most of my time working on customer problems. So really when we look at the uses of superelements, we really look at this from kind of the user's perspective, because that's, in fact, what I am and what most of the people at ATA are. So just a brief outline of what we're going to be talking about today. So really this is meant as a kind of introduction to superelements. So we'll first, of course, address the most obvious question, which is to describe them. We'll talk about the difference between static and component mode superelements, terms that you might hear instead of static. Boolean and static really refer to the same thing, and component mode superelements, Craig Bampton is a term that's thrown around a lot more, and that is one of the methods where you could do a component mode reduction. So you might have heard either one of those terms, and kind of in Nastran's environment, they're for the most part interchangeable. Within Nastran, there are 3 different types of superelements. They're external, part, and bulk data superelements. They really are all kind of a different way for the user to interact with superelements. Behind the scenes, once you hit solve, Nastran is really doing the same thing for all 3 of these mathematically, and the theory behind all 3 of those are the same. And then we'll give a couple of guidelines for using superelements and add some tips here and there. One thing I do want to point out up front is that this is really a 2-day class, and it's a pretty dense 2-day class on superelements, and we're not really trying to condense that into 45 minutes because that would be impossible, really. We're really just trying to give you an idea of what they are, how they can benefit you in your workflows, and whether they can be beneficial or not. You know, there's people who spend their careers developing expertise in superelements and in their use and development. So this webinar is really just an introduction to see whether this is something that can be beneficial for your workflows. Oh, and just in terms of schedule, our goal here is to have about 45 minutes for this webinar and then have about 15 minutes at the end for a Q&A. So just in the interest in getting through all this material, I just would ask that you'd hold your questions to the end, and then we should have plenty of time to address those. So the first thing we need to address, of course, is to say, what is a superelement? So conceptually, it's really just a reduced representation of a finite element model. You start out with a detailed model, you make a reduced representation of that, which has many, many fewer degrees of freedom, but still preserves the accurate stiffness, mass, damping, and optionally dynamic characteristics of that detailed FEM. So the idea is the process is it takes each portion of the model and reduces that independently, and then really into a matrix. And then that matrix, along with a few boundary degrees of freedom, can be coupled together to make a system. So those matrices can either be just a static representation, or it can include some internal dynamic behavior. And then you take that and couple that to the rest of your structure to assemble the system level. So what you end up with at the end of the day, when you start out with a detailed FEM and you do a superelement analysis, you end up with a model that has a combination of physical degrees of freedom on the boundary. So those are kind of normal grids with 6 degrees of freedom. And then if you're doing a dynamic reduction, you also have modal degrees of freedom. And those represent the internal dynamic characteristics. One of the things you'll see sprinkled throughout is this idea that the number of boundary degrees of freedom needs to be small compared to the full-size FEM. If the number of boundary degrees of freedom grows too large, you very, very quickly lose the computational benefit of superelements. So you'll see that throughout. We'll kind of hit that a few different times. So to put all those words into, just into something a little more tangible, this is on the right side here at the top. You have this detailed model of a wing, and it's supposed to be a detailed finite element model. And if that model, let's say it has 100,000 degrees of freedom, by doing a reduction, what you end up with at the end, there at the bottom, is you preserve those 3 grids that are on the boundary, and the rest of the characteristics of that wing is represented just with a few matrices. So you're not able to look at necessarily the nodes anymore. You've done a reduction, so you're left with those boundary grids along with some matrices that represent the internal stiffness, mass, damping, and optionally dynamic behavior of that wing. Superelements are supported in Nastran solution sequences 100 to 200. So there's a very wide range there, statics, buckling, dynamics, even nonlinear analysis, transients, both time to transient dynamic analysis, as well as frequency response dynamic analysis. So there's a lot of different applications for the superelements. So some of the advantages, this is a pretty long list. I'd certainly invite you to read along. I'll hit the high points. So my impression of why superelements were invented was that a very long time ago they didn't have the computational resources we have today, and they wanted to solve models that were too large. So they came up with this process where you can essentially take your model and never have to solve the entire model at one time. You partition the model, solve for, or make a reduction of each portion of the model, and then couple them all back together. And when they're all coupled back together, you can then solve your system model. So it seems like this is less of an issue these days, but it's just something to keep in mind. If you don't have huge computational resources, then this can enable you to solve larger models than you would otherwise. You can sometimes reduce the amount of runtime. Again, if you have to kind of do this in a strategic and smart way. Third bullet there, I think I don't see that one used a lot, but it can benefit quite a bit, is that if you have reduced portions of your model and you want to run trade studies, and the trade studies are confined to one region of the model, if you're using Nastran restarts, then Nastran can be smart enough to recognize that you have only made the change to one small part of your model, so you only have to re-reduce that part of the model. It can reuse previous portions of the model. So that can be beneficial and enable faster trade studies, because you don't have to run the whole model simultaneously. There are ways that you can have partitioned input and output, so that makes for, if you have repeated components, or just to simplify the process of combining models together and then looking at the outputs, that can be beneficial. You can have, if you're in a situation where you have kind of a dispersed modeling environment where lots of different people are developing models, ultimately, someone has to combine all of those, and there are methods within Superelements that can make that quite a bit easier, and just with managing all those dispersed models. Again, nonlinear analysis, same reason is if your nonlinearities are confined to a small region of your model, then you can essentially make reduced models of portions of your model, and if you can live with them being linearized, then that reduces the size of the model that is solved by the nonlinear solver. So again, enables faster solutions. The third to last bullet there, proprietary models without divulging geometry. One of the benefits of this, and this is actually one of the probably largest uses that I've seen, is if you have a model and the geometry of that model is proprietary and you don't want to send that to your customer or your vendor, you can make a reduced version of that model where the only thing that the recipient of that model will see is a few grids in space along with some matrices that represent the behavior. So they physically cannot see what your model looks like. They won't have any idea what the design is like. So that is a pretty big use that we see pretty commonly. And again, back to the dispersed modeling, if you're trying to combine two different models together that you've received from two people, and they use different parameters because they have been correlated to modal test data or something like that, you can't really rectify those two together without using superelements. If you use certain versions of the superelement, you can preserve different parameters on different portions of your model and combine them together. And then the last one is damping. If you know the damping characteristics, again, from a modal test for, let's say, the satellite, and you're coupling that satellite to a launch vehicle, using superelements, you can preserve that damping characteristics and say, here's the damping on the satellite, but solve the whole system of the satellite plus the launch vehicle. Like anything else, there's no free lunch with superelements. There are some downsides. That top bullet there is really just stating what I said earlier, which is that if you have a lot of boundary grids, then that can kind of cancel out the numerical advantage of using superelements. So again, boundary grids, number of boundary degrees of freedom is something that needs to be considered. Just the setup of superelements can be more complex. Like I said, there's no free lunch, so you can reap substantial computational benefit, but that takes a little bit of additional setup time from the user's side. So that's certainly a downside, but it's just a matter of weighing whether that's worthwhile or not. The residual structure, so what you're left with after all the reductions have been created and the models are assembled before solving for the system, that mass and stiffness are generally pretty dense. So for a normal type of structure, usually those matrices are very large but very sparse. With superelements, those matrices are generally smaller but more dense. So that, again, can cancel out the computational advantage. Superelements must be linear, so you are reducing a portion of your model once and then combining them together, so the response of that superelement is always linear. The residual does not need to be linear, and I'll get to what the residual is, but that's kind of what's left over after you've done all your reductions and combined them together. So the way that you combine two superelements together, you could have a nonlinear gap in there or nonlinear spring or something, but the contents and the behavior of a superelement is always linear. And then you do have to make approximations with dynamics for mass and damping because of the modal component mode approach. Anytime you're solving for modes, you always have to decide how high of a frequency to go to or how many modes to include. But that's no different than superelements. So just in terminology, we're not really going to get too deep into the terminology, but this kind of helps frame the idea of superelements. So in this case, you have a wing and you're starting with a detailed finite element model. And when you make a superelement, you first have to decide what are going to be your exterior nodes, exterior points. In Nastran sets, that's called the T-set. You'll see that referred to as the boundary degrees of freedom as well. But basically, that's what's left over after you've done your reduction. So in this case, the interior nodes, or the O set, omitted set, so those are the nodes which you will not be able to visualize once the superelement has been reduced. So in this case, you'll be left with your exterior nodes and a matrix representing the rest of this behavior. Generalized degrees of freedom, so those are the modal degrees of freedom if you're doing a dynamic reduction. So that's where you store those component modes. Again, only if you're doing a dynamic reduction. And then the residual is what is kind of left over after you've reduced all your individual parts and combined all of those pieces together. That's referred to as the residual. The residual is where your system level model is solved, whether you're applying loads or solving for modes or doing a transient or dynamic analysis. Those analyses are done on the residual, which is kind of everything that's left over after you've done your reductions. So one of the approaches is this top-down approach to superelements. So, and we'll talk more about how you implement these top-down, and the next slide is bottom-up approaches. But first, I want to introduce it. So the idea here is that you have a single model of your entire structure, in this case, an airplane. And that single model is valid without superelements, so everything is all connected together the way you want it. So if you're running a superelement analysis, the way that this works is Nastran, you first need to tell Nastran what each superelement is, so what parts go within each superelement. So that's this kind of second partition image here. You can see you've divided it up into wings, engine, fuselage, tail, all those parts. And once you hit go, what Nastran does is it takes those parts one at a time and it creates a reduction for those. So it takes the wing and says, okay, this wing is a superelement. I know where my boundary degrees of freedom are. It puts everything else aside and creates a reduction of just that wing, whether it's static reduction or dynamic reduction. Okay, and then so it's done with that reduction, puts that aside, and it just goes around each piece and does that individually. So does the wing, the engine, the tail, each of those are done individually. So now you can start to see where this kind of reduces the size of the model, because in this respect, Nastran is never trying to solve let's say, for the modes of this entire plane all at once. It's really kind of going on piecewise and working on each individual piece. So, and once it's reduced all these components, it then has a reduced representation of all these, which is several orders of magnitude smaller number of degrees of freedom for each piece. It then assembles them all together. So now this right here is when it's reassembled. Those are a bunch of superelements which have been combined. So each of those individually is very much smaller in terms of degrees of freedom than its original. And you solve the system level model, whatever you're trying to do, solve for modes or anything like that. So this is the top-down approach. There's also a bottom-up approach. The idea here is that you start out with a bunch of kind of disparate models. Maybe these are from different vendors. Maybe you just have several standalone Nastran models. And there's another really partitioning method that allows you to work in this environment where your goal is to build this up as a building block. So you have several models, and you can just essentially stack those all together in one single Nastran deck. So you have different regions of that Nastran deck that say, hey, each of these regions is a separate model. And really, it is as simple as copy-paste with just a little partition line that says where the beginning and end of one is and the other one is. So each of these pieces can be a detailed FEM. Each of these pieces, some of them can be previously reduced external superelements. So that's, again, that proprietary idea that I brought up before. You know, this engine might be a very proprietary thing that the vendor doesn't want to give you. So they can give you a superelement, an external superelement of that engine, and then you can attach that to the rest of your structure and solve for system modes. Dynamic reductions, I've kind of referred to these terms earlier. The two type reductions, one of them is static. You'll see static and Boolean, those are really the same thing. When you make a static reduction, it is exact in terms of the mass and stiffness. So you lose nothing, there's no loss of accuracy between your boundary points. But because, as the name implies, it's static, so it does not attempt to represent the internal dynamic behavior. So it can be very beneficial when used appropriately because it reduces the size of the model and there's no loss of accuracy there. So the second one is a component mode synthesis method, and that's a dynamic reduction. And what that does is it takes your static reduction and really just adds component modes. So the idea is that will enable you to represent the dynamic behavior of your component. So the way that it's done in Nastran, superelements are really based on the Craig-Bampton method of component mode synthesis. So you don't need any special DMAP alters or anything like that. That's kind of, it's just the built-in method. And they have the idea there is when you solve for the component modes, all your interface degrees of freedom are fixed, which is, in Nastran speak, it's the B set. In Nastran, you can release some boundary degrees of freedom, which again is called the C set. It's not a Craig-Bampton reduction. It's a more general version. It's still using component modes. It's just, it doesn't fit the criteria for what a Craig-Bampton reduction is. So the question is, well, which one should you use? So a dynamically reduced model will be accurate for statics because it includes a static reduction. So it's just going to, if you make a dynamic reduction and use it in a static solution, it'll still be correct. It'll just ignore those modes. Of course, you've spent more time up front solving for those modes. The trade-off is not necessarily true. A static reduction is not necessarily accurate for a dynamic solution. And as the name implies, we're not trying to represent internal dynamics, so it's not necessarily going to be worthwhile. A very rough rule of thumb for how many modes to include in your dynamic reduction is about 1.5 to 2 times the frequency content of the system level, of the frequency content of the system. So if you want your system level modes to be accurate to 100 hertz, very rough rule of thumb is say, well, we'll go to 200 hertz for your component. I wouldn't write that down as gospel. That certainly is like it's implied. It's a rule of thumb. There's lots of other considerations that go in, but that at least gives you a ballpark estimate of what you need to do when doing a dynamic reduction. So in Nastran, there are 3 partitioning strategies. So there's an external superelement. So this is where you're not really trying to solve for a system. You're just trying to make a reduced representation of a portion of your model, and then you're stopping. So you're not trying to do a system level analysis. So this is convenient if, you know, I call this kind of a one and done reduction. So if you just want to reduce a portion of your model and you never really want to have to deal with the interior nodes and elements again, this is a convenient way to do it. It's certainly convenient for transferring a proprietary model. So you can make a reduced representation of that aircraft engine, preserve the boundary points where it ties into the fuselage, and just send it off to your vendor or your customer. And that way they can't see what's inside. Another method is part superelements, and this is more of your bottom-up approach. So you're basically starting with several independent FEMs, which are totally complete and standalone on their own, and you're just stacking those together inside of a single Nastran deck. So you use begin super cards as a partitioning line. And the convenient thing here is that since each piece is standalone, you don't have to worry about duplicate IDs against across superelements. That's okay. And really what this is kind of a compromise between the bulk data and the external superelement approach. So that enables you to just stack multiple decks together. Main bulk, I think this is the most common superelement approach. It's when you have a single FEM which is complete and is valid without superelements. But what you, the user, are doing are partitioning that and telling it what portions of that model are inside of each individual superelement. One thing to keep in mind, these 3 different strategies, behind the scenes, once you hit go, Nastran really uses the same theory, the same approach, the same reduction methods for each of them. These are really just 3 different ways that the user can interact and can partition the model. So just keep in mind, these are more from the user side. These differences exist from the user side, but behind the scenes, all the mathematically, it's all the same. So what is an external superelement? So this is either a static or dynamic reduction. And again, this is where you're making the reduction and stopping. So starting with your wing here, you are starting with a detailed FEM, form a reduction, you preserve the boundary degrees of freedom, the boundary grids, and what you end up with at the end of the day is 3 nodes which appear to be floating in space, but really there are matrices that define the mass and stiffness and potentially dynamic behavior of those modes, of that structure. You can take this external superelement, and you can attach it to another structure using part superelements, and I'll talk more about that in a moment. You can include data recovery. So just because you're reducing those out does not mean that you cannot extract output. So if I'm interested in, let's say, the torque on one of these control rods, You could, while you're doing the reduction, you could just ask for a spring force or a bar force. And what Nastran will do, it'll write what are called data recovery matrices, so that once you have this reduced superelement, it can recover for you what that torque is based on the deflection and loads going into these boundaries. So by using an external superelement, it's not that everything inside is opaque anymore. You can still use data recovery matrices to get those out. There are several formats available. They're functionally all the same. They're just, they're just slightly different usage and different formats. But again, they're all basically the same. And one of the benefits to external superelements is you don't need any special licenses to create them. So you can always create them to hand them off to someone else if that's necessary for your workflow. Several of the formats here, again, these are functionally the same, but there's MAT-OP4. So this writes outputs to the output 4 format, which can be either ASCII, formatted, or ASCII, or it can be in binary format. And it writes some of the grids and interface data unique to the punch file. And that's really the most common format that's used in the coupled loads community, which is primarily in aerospace analysis out there, but there are other industries that use that as well. Another format is the DMIG OP2. So in this case, all the data is written to the output 2 file, which is a binary file. And the benefit of this is everything is all kind of located in one location, and it's full precision, so you don't lose any data there. There's another version, the DMIG punch. So in this case, your matrices and your grids, your boundary grids, are written to the punch file in DMIG format. So these are ASCII, and so you can open up the ASCII file and just look at it, and it physically makes sense what you're looking at. This one is very flexible. One of the benefits of this is that you can actually attach these matrices to system-level structure without using a superelement license. It's kind of old functionality from Nastran that they have not removed. I'm not letting the cat out of the bag here. This is something which is in the documentation. There is some loss of functionality. So, for example, if you do this without the superelement license method, you can't do data recoveries from inside. So there are trade-offs, of course, but that's a pretty convenient way to attach a matrix to some other structure, and if you don't or can't use superelements to do that. And then the last two, the MAT-DB and DMIG-DB, these are, everything is written to the master and dball binary files, which can be very, very large files. So those aren't used very much, but they are there. So just to give you a sense of how to create an external superelement, this is a sample deck here, and the black text is what you would have if you were just solving just kind of a regular modal solution, solving for the modes of this sample. Everything in red is what you would need to add to create an external superelement. In this case, it's the MAT-OP4 option. There's slight changes for the other options, but it's pretty straightforward. You need to first specify a file where everything will be written out. You need to give it a case control command. This is ext_seout command. That's what says, hey, make me an external superelement, and some of the parameters are set there. VSetCar here, this is just defining what the boundary grids, degrees of freedom, will be. And then in this case, we're doing a modal reduction, so we are setting up S points and Q sets. Those are the modal degrees of freedom where component modes will be stored. So that's if you like getting your hands dirty in the deck. If you're doing this from within CMAP, starting with, again, a regular modal solution, you just set up in the analysis manager, you set up take your modal solution analysis set, and if you expand master requests, you can get to this external superelement creation form. And it's really just set up several of the settings in here. These are all the things that you see on the ext_seout case control command. You can also automate the creation of your modal degrees of freedom S points. So you could do this it's pretty streamlined in FEMAP. Similarly, in NX Nastran, you could set up a solution, and there's a Sol 103 superelement and a Sol 101 superelement. Again, same idea. You need to first create your boundary degrees of freedom, either fixed or free, set up some superelement options, and tell it, in case of a modal solution, how many modes to solve for. So it's supported across all the preprocessors. So that's kind of the end of external superelements. So part superelements. Just wanted to talk about these for a few minutes. So this is, again, it's just a model partitioning strategy where you take several different FEMs, independent FEMs, and you stack them all together into the same deck. So again, you don't have to worry about numbering IDs across superelements. You're allowed to have duplicates. And what you do as you kind of copy and paste these into a Nastran deck, you use these begin super cards to define the partition. So that's what tells Nastran where the end of one superelement is and the beginning of the next one starts. And each of these pieces, they can be a detailed FEM with nodes and elements and materials, or it can be a previously reduced external superelement. What Nastran does to connect these superelements together is it's purely geometry based. It just looks for grids across superelements that are coincident within some tolerance. And if they're within some tolerance, it says, oh, these must be attached. So it essentially ties them together. So it can do that totally automatically. You optionally can completely make the process manual of connecting those all together, or any combination of those two. Again, these are used to combine previously reduced external superelements.
I'm good.
So I've kind of talked about some of this already.
Right.
You know, you have parts.
The webinar.
So I'm getting some crosstalk. I think someone must be on the phone. If you wouldn't mind muting, please.
I am, yeah. Yeah, very much.
Okay, there. So begin super, in every Nastran deck you start with begin bulk, and everything from there to the first begin super is in the residuals. That's what will be kind of remaining after all reductions are complete. Once you see the first begin super, everything between the first and the second begin super, or the first begin or a begin super and end data, that just defines the partitions in each superelement. So I have a sample here. The idea here is you have begin bulk and you have a FEM and several other kind of normal types of cards. And these are FEMs that are in the residual. So again, after you've reduced all the superelements, you tie them together with everything that's in the residual. So in this case, the bus will still be in the residual. And there are various cards here that do various things and set up modal degrees of freedom and define the superelement tree. And then we have the first begin super. So now Nastran knows that everything between their first begin super and the next one, this is all superelement 100. And in this case, to highlight it, I've added param weight mass. So I've added something to scale all the mass entries to get them into mass units. So then we have the fairing. And then there's another begin super. And here I've changed, again, to highlight it, I've said, well, okay, this payload needs to have the non-default coupled mass formulation. So this is completely compatible. This is completely okay to do in part superelements. Without part superelements, you would have to pick one or the other, and you'd have to probably modify one of your models or accept some inaccuracies in one of your models because you can't use different parameters within the same, with other partitioning strategies. So some of the advantages of part superelements is that really what part superelements does is it streamlines the process of creating several external superelements and then attaching them all together. So that's really the main benefit, is that you can complete a system level run all at once without having to stop, create an external superelement, and attach that in together. Certainly it can help attaching FEMs from different vendors. Maybe they used overlapping number IDs and you don't want to have to deal with renumbering. And all you really got to worry about is where are the interface grids located, just the location of those, not the IDs. It's pretty easy with part superelements to tell which portions of your model are within which superelement, because it's right there in the Nastran deck. Just look for your begin bulk statements, or sorry, begin super statements, and that defines it for you. You can instance parts of your superelement. So if you have two reflector arrays, instead of having Nastran reduce one and then reduce the other, even though they're identical, you can use that SE-loc bulk data card to say, take that take that reflector that you've already reduced and make another instance of it over here in this other location with being reoriented. And then with part superelements, if you have the full FEM, you could do any data recovery you want. With an external superelement, you have to decide up front, what outputs am I concerned with? Because you create those data recovery matrices when you create the reduction. If you have the full FEM in a part superelement, you can change that from one run to the next. You could decide you want to look at element forces on one run and displacements on another, because, again, all the detailed FEM is still there. And the last partitioning strategy are main bulk superelements. So this is the idea where it's a top-down approach, where you have a single FEM which is valid without superelements. And for whatever reason, you decided that it would be best to use superelements, all the advantages I listed up front here. And so you, the user, are just telling it which grids will be interior to each superelement. So once you define the grids that are interior, Nastran goes and finds where the boundary grids are on its own, and then goes through the process of reducing each one individually and coupling them back together. So this is kind of the traditional approach. Most people who use superelements use main bulk superelements. So that's the one that most people, I guess, have talked about. And this just gives you an idea of what a main bulk superelement looks like. So you have a modal solution, and this now is your entire FEM, and all you've done here is you've defined cards that the SE set cards define what grids or what degrees of freedom are inside of each superelement, and then you have to set up the modal degrees of freedom if you're doing dynamic reductions. But the idea here is that if I were to strip out all these red cards, this would be a perfectly valid model as is. So trade studies, with either part or main bulk superelements. Again, those are just the way that the user interacts with it. This trade studies with restart, this is valid across main bulk or part superelements. But they can make design studies much more efficient. So the idea is if you have this model of the airplane and you are running trade studies on, let's just say, some spring stiffness on a control surface, for example. Without using superelements, every time you change that, you'd have to start from scratch. Even though you've only changed what are probably 5 or 6 terms in your stiffness matrix, you have to start from scratch with everything. So with using restarts and superelements, you can get very significant computational benefits and really just speed. You have to kind of think about this up front a little bit, but the idea is if you're using superelements, let's say you've already solved for the modes of your structure. So again, what Nastran has done is it's solved for the modes of each individual piece and then couple them all together and solve for the modes of the whole structure. Let's say you want to change that spring stiffness now. So you just go into your deck and you just change a spring stiffness and you say, I'm going to use a restart. What Nastran does is it'll look at this wing and say, hey, has anything changed? Have you changed anything in this wing? And if the answer is no, then it'll say, okay, well, I have already reduced this. I'm going to go grab that from my master or dball database. So it doesn't have to re-reduce the wing. And it goes across the whole model and looks at each superelement individually. And if it sees, oh, you've changed the spring on the tail. Okay, so I do need to re-reduce the tail. I have to start from scratch with the tail. And once it's reduced the tail, it adds that to all the existing superelements and then just solves for the system level behavior. Remember, the system level has many, many orders fewer degrees of freedom than the sum of all the individual pieces. So I don't see this utilized a whole lot with restarts, but this can be very beneficial just in terms of speed and computational efficiency to get through lots of runs with this. Just a couple of comments on what you should think about when figuring out how to partition a structure. Computing resources, of course, are important. You should try to keep each individual superelement so that it'll fit on whatever machine you're running. In general, you want to use logical partitioning strategies. So, for example, for this little mock-up satellite, it wouldn't make sense to try to chop the purple bus right in half. At natural structural boundaries. So you might have a boundary here at the solar arrays, maybe at the reflectors. Just kind of logical partitions are in mind. And again, you do want to limit the number of grids that are on the interface. Again, because that can really counteract the benefit of superelements. If part of your model has already been correlated to test data, that would be a good place to partition, because if I have already done a modal test on the solar array and I know what the component modes are, and I know what the component of damping is, by partitioning it at the base of the solar array, I can assign damping to those component modes, which again are correlated to a modal test. Again, if you're going to be doing restarts, keep that in mind. So if all your trade studies are going to be done in one portion of your model, if you try to keep that in the residual or close to the residual, then that can be beneficial to minimize the amount of essentially rework that Nastran has to do. And then, of course, you have to think about whether you're going to be doing static or dynamic reductions for each portion of the model. So just a summary and, just kind of a recap, really. Superelements, I hope that after kind of seeing and hearing about some of this, that you're thinking about some of the ways this might be applicable for your workflow, to speed things up, to make things more efficient, or to enable model sharing a little bit easier. Static and dynamic reductions are both supported in NX Nastran. You can use Boolean or Craig-Bampton reduction methods. And then the three different superelement methods. So there's external, where you are making a reduction and stopping in order to hand that off to someone else or to attach it to some other model. Or parts or bulk data superelements, where you're really doing kind of system level analyses. They're just different ways to define the partitions between the superelements. And then again, this is kind of, if there's one thing you take away from this, it should be this last bullet here. So you really need to try to keep, minimize the number of nodes at the boundary. And it's hard to give a rule of thumb on this because it depends on a lot of different things. But if you have more than 50 grids, or even that's a very high number. If you have more than 50 grids on a boundary, then that might be way too many. I mean, typically, if you can keep it down in the tens or fewer, that would be better. Of course, that depends on your structure and how different types of structure, of course, have different amounts of coupling. But just to throw out a number, 50 grids is a pretty big number already. So that's all I have. Just want to thank everyone for signing in and participating. I guess I'd love to open it up to any questions that anyone might have. I think some people have been muted here. Any questions, anyone? Okay. Dan, do you have any parting comments?
I do not. Thanks a lot. Very impressive. And if anybody has any questions or whatsoever, please feel free to contact us at the contact information up on the screen. Also, we recorded this. I'm sorry, George. Geez, I guess I do have some end comments. Also, we recorded this, so this will be available online for any of your friends or counterparts that missed the live broadcast. We'll have this probably on the next day or so posted to our website.
Okay. Well, thank you, everyone. Have a good day.